right, welcome to your stats class. So my advice would be to try these problems on your own first, all right? Work through the packet, give each one a shot, and then come back and check this, listen to the explanations. Don't just like see if you got the answers right. Listen to the explanations so that you're in the best place possible to be successful on the upcoming quiz. So below are histograms, the values taken by 3 sample statistics and several hundred samples from the same population. These histograms estimate the sampling distribution. The true value of the population parameter is marked on each histogram. All right, so the bars are your sampling distribution. And this point right here is the true population parameter. All right, so it says which statistic has the largest bias among these 3? So you have to know what bias means, and then you have to be able to look at the graphs and kind of understand it. So unbiased, we'll start with that, is when the center of the sampling distribution and when I say center, I'm really referring to the mean. All right, when the mean of the sampling distribution is equal to the population parameter, which is the true population value, and bias would be the reversed. All right, so a biased estimator is one where the center of the sampling distribution is not equal to the population parameter. All right, so on each of these, they're telling us where the population parameter is. All right, that's our population parameter, that's our population parameter. And we're saying which of these has its center furthest from the population parameter, because it's asking for the largest bias. So if we look at A, that's pretty well centered over the population parameter. So this one is likely to be unbiased. All right. Now this one's not quite symmetric. We seem to have more over here than we have here. So it might not end up directly on the population parameter, but it's probably pretty close. Whereas this one, the peak of our curve is actually over here, and the population parameter is over here to the right. So if we're looking for the one that has the largest bias, the answer would be C. All right. The center of the sampling distribution is to the left of the population parameter. All right, so next question says, which statistic has the lowest variability among these 3? So variability, we're basically talking about spread / standard deviation, right? And you obviously don't need to calculate that, but you can just kind of eyeball it. And I would say that A has the lowest variability because most of the sample statistics let me move that paper up so you can actually see it. So A, most of the sample statistics are condensed in just a few bars. All right, so the bulk of A is really just in these few bars. So it's very condensed versus here, we're much more spread out. We've got more area to the right and to the left. Same thing here. This one has a little bit of a tail to the right. So things are much more spread out. So A would definitely be the one that has the lowest variability or the lowest standard deviation. Last part, based on the performance of the three statistics in many samples, which is preferred as an estimate of the parameter? All right, so these all represent different statistics we're calculating. We're trying to get to the true value of the parameter. Which one do we want? All right. Now, there's kind of two things that you're generally looking for. You need it to be centered on the right value. Otherwise, it's not really useful. And ideally, the lower the variability, the more often you're going to be accurate, right? You're not always going to be accurate, but you're going to be accurate more often, right? And based on those two factors, again, the answer would be A. It has a low variability and the center of the distribution is the same as the population parameter. Right. So it has low variability and the center of the distribution is the same as the population parameter. All right, so this is an example of sort of like conceptual questions. All right, it's not the actual like calculate percentages, calculate probabilities, use your formulas, but this is sort of understanding the concept of a sampling distribution and what we're trying to use it for. All right, we're trying to use it to estimate the true value. And we know that when we take a sample, it's not always going to be that true value, but we're hoping that on average, if we take lots of samples, they will average out to be the true value. And in a situation like this, they will, because it's centered on the true value. On a situation like this, even if you take thousands of samples, they're going to average out to the wrong value. So this is a bad estimator. All right, this one will probably average out to pretty close to the right one. But again, there's way more variability here. So yeah, on average, it'll be right. But on any given sample, you could be quite a bit off in either direction. Where in this one, it's pretty rare that you're going to be too far off. Most of the time, you're going to be right where you want to be, which makes it the ideal estimator out of those three. All right, so let's take a look at some that are more kind of calculation-based. All right, a study of college freshmen study habits found that the time in hours that freshmen use to study each week follows a normal distribution with a mean of 7.2 hours and a standard deviation of 5.3. So, sorry, but a whole bunch there got in the way, but this is 5.3 right there. For those of you online, that won't be an issue because there won't be a whole bunch. But anyways, these two values right here are our population parameters. All right, so we have this population of college freshmen, and they have a mean of 7.2 and a standard deviation of 5.3. It says, can you calculate the probability that a randomly chosen freshman studies more than 9 hours? If so, do it. If not, explain why not. So in this case, we can, because the problem tells us it's a normal distribution. So can we calculate it? Yes. We're told the population is normal. Right now, in terms of actually calculating it, that's just where we use our NCDF. So we're doing an NCDF from 9 to 9999 when the mean is 7.2 and the standard deviation is 5.3. All right. So NCDF 9 to 9999 when the mean is 7.2 with a standard deviation of 5.3. Right, and we get 0.3671. So 0.3671. So roughly like a 37% chance. Now, what is the shape of the sampling distribution of the mean X bar for samples of 55 randomly selected freshmen? So that's basically saying, what is the shape of our sampling distribution? Of the sampling distribution. All right. And this is that little activity we did with the computer program where we were selecting chickens, but we know that the shape is going to be normal. All right. And part of the reason we know that, and it turns out it doesn't actually even matter for this problem, but our sample is above 30. So according to the central limit theorem, the sampling distribution will be normal even if the population is not. Now, the next question says, does the size of the sample matter in this case? It actually doesn't, all right? No. We don't need a large sample because our population is normally distributed. All right. When it's not normally distributed, that's when the sample size comes into play. But we're fine here. Our population was normal. So whether or not our sample size is above 30 isn't really relevant here. So what are the mean and standard deviation for the mean number of hours X bar spent studying by an SRS of 55 freshmen? So that's basically saying, what is the mean of X bar, which we know is going to equal the population mean because it's an unbiased estimator, which means it's just going to be 7.2. Now, what's the standard deviation of X bar? Again, we're sampling without replacement, which is pretty much the way you always sample in the real world. But sample is under 10%, so we're okay. All right, that's where that 10% condition comes into play. 55 people, as long as there's 550 college freshmen, you're fine. So we're probably going to be fine in this case. So we can just use our formula, which is the population standard deviation divided by the square root of n, or in our case, 5.3 divided by the square root of 55. All right, so 5.3 divided by the square root of 55 is going to give us 7.147. Right, now that we have those numbers, we can answer this last question. Find the probability that the average number of hours spent studying by an SRS of 55 students is greater than 9 hours. So again, sometimes kids get confused because they're like, wait, isn't that the same question? This is for a single student. This is looking at the average of a group of 55 students. All right, so when we take these 55 students and average their study time together, what are the chances that their average is above 9 hours? Again, it's going to be smaller. All right, it's not strange to have one person that's studying that much. It's going to be much more unlikely to get 55 people that average out to above 9 hours. So 9,999 when the mean is 7.2 and the standard deviation is the 0.7147 that we calculated up above. All right, so distribution menu, normal CDF, 9 to 999. 7.2 stays the same. The only thing that changes is the standard deviation. It drops to 7147, which again is going to make our probability a lot lower. We're down to 0.0059. Right? But this is one of the long answer type questions that you need to be able to do. All right, let's take a look at the other type of long answer question that you're going to have to be able to do. So a friend has offered to play a gambling game with you that involves flipping a coin that he has provided. Since a flip of a heads will be to his advantage, you want to test the coin for fairness before you begin to play. Your friend is willing to let you flip the coin 50 times to determine if the probability of getting the heads is actually 0.5, as it should be if the coin is fair. So we can think of this 0.5 as our population parameter, right? That's what a coin should be, right? And in this case, our population parameter is not referring to a mean, it's referring to a proportion, which means we're using different formulas. All right, so assume for a moment the coin is fair. If p hat is the proportion of heads in 50 flips of the coin, what are the mean and standard deviation of the sampling distribution of p hat? All right, so we're looking at the mean of p hat, which should equal the true population parameter. All right, this is the population parameter. All right, when we don't put the hat over it, that's the population parameter, which we just stated was 0.5. All right, the problem gave it to us. So the mean of all of our samples should be 0.5. And the standard deviation of p hat, the standard deviation of all those sample results, is found using the formula PQ over N. Now, in this case, if P is 0.5, Q is also 0.5 because they have to add up to 1. And our sample size is this 50 here. That would be our N. So we're dividing by 50. And then we just have to put that into the calculator. So 0.5 times 0.5 divided by 50. And then we're going to take the square root of that. All right, so 0.0707. Explain why you can use the formula for standard deviation of p hat in this setting. All right, so normally we'd be looking at the 10% condition, but flipping a coin is not sampling without replacement. All right. Each flip is truly independent, like the probability is not changing. So the 10% condition is not necessary. Right? Normally, when you're sampling without replacement, the 10% condition, is not necessary. Normally, the 10% condition says, your sample has to be less than 10% of the population. All right, but flipping coins doesn't really have a population. All right, the odds governing the flip of a coin don't change from flip to flip. Each one's truly independent, so we don't even have to worry about that condition. In contrast, when you're, pulling people out, each time you pull somebody out and select them from your sample, you've slightly changed the odds of everybody else being selected. And that's where the 10% condition starts to matter. As long as your sample is under 10% of the population, we say, yeah, the numbers are going to shift, but the shift is going to be so small, we don't care. The example I like to use is pretend you're picking, males and females from the world population, right? Once you take that first person, if it's a female, technically the odds of getting another female have changed because there's one less female in the world that you can select, but the difference is so small we don't care. That's what the 10% condition usually refers to. Here, we don't have to worry about it because there is no population of coin flips. Each one is truly independent, so the probabilities aren't changing from flip to flip. All right, so you flip a coin and get 30 heads. Do you risk insulting your friend by refusing to play with his coin? Support your answer with an appropriate probability calculation. All right, so we're going to use the normal distribution. And to use the normal distribution, we need to first make sure there are at least 10 successes and 10 failures. All right, and not observed, but expected. So that means we're going to do n times p, and we're going to do n times q. I mean, we can observe that they got 30 heads and 20 tails, but we have to use the expected values. So we do 50 times 0.5. We do 50 times 0.5. Those are both 25. Those are both 10, above 10. So they both check out. All right, so that says we can use the normal distribution. Now we're actually going to use it. So we observed 30 out of 50, aka 60%. So we want to know what were the odds, because 60% is above what we would have expected. What were the odds of getting 60% or higher when we expected to get 50%, and the standard deviation for a sample of 50 flips is 0.0707. All right. NCDF 0.6 to 9999. Why do I keep doing that? When the standard deviation is 0.5, sorry, the mean is 0.5 and the standard deviation is 0.0707. Okay. And it works out to be 0.0786. 0.0786. So a lot of times we use a cutoff of like 5%. So we could say it was unlikely, but not totally unbelievable, we'll say. Again, that's 7%. It's kind of right on the edge there of kind of like, I don't feel great about this, but I don't have overwhelming evidence that the coin is fixed or weighted in some way. Okay, but gist of this, not so much the coin part, is knowing how to come up with these numbers, knowing how to use these numbers inside of an NCDF, and being aware of the different conditions that have to be in place to do all of this stuff. Okay. So let's take a look at the last one here. Actually, there's two on this page, but the last one's really quick. Teenagers send many text messages. Recent polls cite medians of more than 50 per day. Consider a large population of teenagers for whom the distribution of the number of text messages sent per day is strongly skewed to the right. Here's the 5-number summary for the number of texts per day for this population. All right. So right here, these are all parameters. All right. They're saying for the population, this is what we found. We found that there are teenagers that send 0. There's teenagers that send a max of 250. And then the quartile 1 is at 20, the median is at 55, quartile 3 is at 140. Now, below that, suppose we take a random sample of size 32 from this population and calculate Q1. So we're taking a sample of 32, finding Q1 from that sample. Below is a dot plot of all of those Q1s we calculated from 50 such samples. So this is effectively our sampling distribution. All right. These right here are our parameters. This is our sampling distribution. So what does the dot at 35 represent? All right. That is a single sample of size 32 where the Q1 was calculated to be 35. All right, so each dot represents a different sample and the Q1 calculated from that sample. All right. The next question says, do you think your estimator is biased or unbiased? So again, unbiased means the center of the sampling distribution equals the parameter, all right, which is center is another way of saying mean. And this is saying that the center does not equal the parameter. So biased is saying the center does not equal the parameter. Sampling distribution center. Sampling distribution center does not equal the parameter. All right, so that's the difference between biased and unbiased. Now, if we look at this one, all right, the true value is 20. All right, so 20 right here is the population parameter. All right, and we know that because it tells it to us up here in the problem. That's our population parameter. So what we're asking ourselves is, if we took each one of these dots and averaged them together, would they average out to 20 or would they average out to something else? If they average out to 20, our estimator is unbiased. If they average out to something else, our estimator is biased. So if we were to look at this and ignore the outliers, we'd probably say, yeah, that's unbiased. You know, it's probably going to average out pretty close to 20, but we do have these points over here, all right? We have these points over here that are going to drag up that average. So because of those points, this estimator is probably going to end up being slightly biased. So we'll say probably slightly biased because the outliers will raise the mean of the sampling distribution above 20. And again, 20 was the population parameter. All right, so since these dots are not going to average out to 20, all right, we identify that as a biased estimator. All right, probably not super biased in this case, but it'll still be biased because of those outliers dragging up the mean of our distribution here. All right, number 5, last one here. For the description below, identify each underlined number as a parameter or a statistic. All right, so I don't know if I had that showing or not when I was writing it, but basically I said probably slightly biased because the outliers will raise the mean of the sampling distribution above 20, and again, 20 represents the population parameter. So for this one, basically we're looking at the underlying numbers and identifying them as either a parameter or a statistic. And basically, this is just a vocab question to make sure that you realize parameter is dealing with the population and statistic is dealing with the sample. All right, so a 1993 survey conducted by the Richmond Times-Dispatch 1 week before Election Day asked voters which candidate for their state's attorney general would they vote for. 37% said they would vote for the Democratic candidate. On Election Day, 41% actually voted for the candidate. So 37% is from their sample. So that represents the statistic. Statistics are from samples. And 41% represents the parameter because that's everyone who actually voted. So in this case, that would be our population. All right. So hopefully this was of use for you. Hopefully this will put you in a good place for the quiz that we're going to take on this material. Again, there's sort of the conceptual questions here of just understanding what a sampling distribution is, how we're actually using it, what's ideal in a sampling distribution. Again, this question's kind of getting at that same sort of idea, like, do you understand the idea between a biased and an unbiased estimator? And then there's the more straightforward, here's the numbers, here's the settings, calculate your sampling distribution, mean, and standard deviation, and then use it inside of an NCDF, right? And there's one set of formulas we use for proportions, and there's another set of formulas we use for means, right? And keeping those straight and using the right one in the right setting. Other than that, if you have any questions, just let me know, and we'll go from there. Have a great day.